All right, I'm trying to record a help session here. Hopefully this is helpful to you. If you watch it, maybe let me know in class that it's beneficial. I'll keep doing it. So this video will cover homework 4B, some general questions that I think are important, and then I have some students here that may have some questions that come up as I go through some problems. So this chapter is on properties, property relationships, and this particular homework focusing on using the tables. This problem has an image of the saturation tables. There's two saturation table problems. One that the first column is in even temperature increments. The other table is in even pressure increments. So sometimes, depending on the givens, you may choose one table or the other. The question here is determine the pressure in bar of saturated liquid at 156.09 degrees C in the table below. So saturated liquid is actually, tells us one of our properties. If we look at the quality for saturated liquid, the quality is 0, and then the temperature is 156.09 degrees C. And then we need to make sure what the substance is. It's water. So we need to go to the saturation tables for water. Given our temperature, it might be possible that the pressure is the table to go to, but we can start here with temperature. If I scroll down and see that 160 degrees is there, so we're close to that value. Now, the way this problem was set up, though, it randomly picks temperatures, so I know that it's not going to be an even value in the pressure tables. But if for some reason I thought maybe it's an exam question, I might flip over to the pressure tables and just see if in the pressure table it lists under, like, say, 6 bar, so possibly at 6 bar, the temperature might be close, the saturation temperature might be close to 156.09. So that would at least be worth a try. But we'll do the interpolation. So I have temperature of 140 degrees and 160. Let me leave a little space. And my 156 is between those two values. So I always want to make sure that my value is in between these two values. So I'm doing interpolation. Rather than at 163, I would be outside that range, and it would be called extrapolation, which generally isn't going to be very accurate. Then I have the thing I want is the pressure. So the next column is pressure in bar. And I have two values. At 140, it's 3.613. And 6.1785. So just kind of visually inspecting that, that's about 2.5, the difference. And over here, I've got a 20-degree difference, and about the smaller value is about 4. So I'm about 1/5 of the way from this lower value to the upper value. So 1/5 of that would be about 0.5. So I'm guessing it's going to be about 5.7, somewhere around there. So that's just a guess. If I end up finding it's 3.9, I probably did it wrong, right? So sometimes just visually inspecting, but generally we want a more accurate answer than that. So let's do it in terms of an equation. So let's call this position 1 and position 2, right? Or I think actually in the handout I have for the class, I called this like a U and an L for upper and lower in terms of the rows. So T minus TL over TU minus TL. And then you need to make sure, whichever one you call upper and lower, it doesn't really matter, but you have to be consistent. So then I have P minus PL over PU minus PL. And it doesn't mean the higher and the lower value. Sometimes the two go in opposite directions. So here the temperature's going up. If you have a variable where this is going down, if you take the larger minus the smaller, you don't want to think that way. Just think of the upper row and the lower row, or the top row and the bottom row, or row 1 and row 2, either way. So then I figure out, well, what are my knowns? My knowns, 156.09. And then I'm going to use the lower row, minus 160, over the upper row, which is 140, minus 160. And then what we find out is, well, we're going to get two negative values, but it won't change the answer. And P minus 6.1785.
Sir, why don't you do 156 minus 140? Because that'll give you a wrong, like the 140 to the...
Right, so if you decided I'd rather do T minus T upper over T lower minus T upper, you could do that. But I picked that without looking at the values.
But it still works the same way?
Yeah, it would give you the exact same answer.
It won't give you like a negative because you have 156?
No,
oh,
no,
so
it's fine,
okay.
it'll cancel. So whatever you decide, if I want to call this 1 and 2, it doesn't matter as long as I stick to the same for both sides, I stick to the same thing. But so in this case, since I didn't try and figure it out by which ones would give me positive values, and unfortunately what happens is students just want to make them positive, then they make one of them positive, and if the other is going in the other direction, they make that positive, and it should have actually been a negative correlation, and then they get the wrong answer. So whatever you choose, you need to be consistent, but so I'm just gonna stick with what I started with here, even though I end up with two negative numbers. Anyway, we could try both of them, and then I have one equation, one unknown. Right?
Would it be the same thing if you did 160 minus 140 over 156.09 minus 160?
Okay, so let's try it both ways. So now I say, instead of doing it that way, I want to say
It's the same thing.
Yeah, it didn't be the same thing, no?
Yeah.
right? Then all the values will be positive, right? I think what you want to be careful is you don't just look over here and say, well, I want my values to be positive, and then you come over here and you see, oh, well, these are in reverse. So if this was 6 point something and this was 3, then you go the other way on the other side. That's a bad idea. So you can take this value minus this one, divided by this minus this, but then you have to do the same over here. This minus this over, do it the other way. So I'll write it that way as well. So now T is, well, and now I'm going to write P minus 3.613 over 6.1785 minus 3.613. Right? And I should get the exact same answer in either case. Right? So you have to decide which way you want to do it. I tend to do it the other way, so I just systematically take my value minus this one divided by this one minus this one. If you like doing it the other way, if you're generally always working with temperatures, then maybe it makes sense to go the other way, right? But it makes no difference. What you can't do though is make this one lower and then put lower minus upper, right? That's gonna throw things off. I guess technically if you were consistent here, that would even work, but I would strongly recommend that you keep them the same on both sides, and then just follow that convention, right? And not try and switch it to make things positive. So I end up with a negative over a negative, right? So it's positive, so it's this difference, which is -4 over -20, or -5 over negative 4 over -20, and then here I get a negative number, so the numerator is gonna have to be a negative number, but both sides are negative, so I'll get P equals positive number, right, between the two. And I'm guessing I will get, you do it, 5.587. Right, and I don't know, we'll do another example, and I'll do it the other way, where I get positive values and positive values.
What's easier?
All right, so let's move on to another question. This is a good one. This is a little different. So
Do
this,
you want to put on the board problem 2 or something?
sure. So let me. Okay, let's try it again, and this time I'll use the value minus the upper row over the lower minus the upper, and we'll end up with positive over positive for the temperature anyway. In this case, I'm again trying to find the pressure. I'm not going to finish this problem because this one's not that interesting. So I have quality, so it's water. This time it doesn't tell me whether it's saturated or superheated directly, but we're given two things. The quality is 0.32 and the temperature is 204.1. So anytime a quality is given, the quality is only defined between 0 and 1. And so if quality is given, it's a saturated liquid vapor mixture. So we know because quality is between 0 and 1 and it's given, then it's a saturated liquid vapor mixture.
So the other one, since the other one said it was automatically saturated liquid, we don't have to.
Well, the other one, it didn't say it was a saturated liquid vapor mixture. It said it was a saturated liquid. So we know the quality was 0. If it said it's a saturated vapor, the quality is 1. If it says the saturated or the quality is something between 0 and 1, then we know it's a mixture of liquid and vapor, right? But in all three of those cases, we're in the right table. It's sort of given away because in the homework problem, the table's right below the question, but normally it wouldn't be. So now this is really no different than the last problem, because what you notice is there's only one pressure given for that temperature, right? So if I go down to something that brackets 204, I have two values. T equals 200 and 220. And my value is 204.1. Right, so now I'm closer to this value, and I'll draw my little diagram the other way. So I'm going to take my value minus the upper value this time, divided by the lower minus the upper, and then I'll get positive values in the numerator and the denominator. So I'm going to
When
have.
they give you the quality, does it affect the outcome?
It doesn't. That's why I'm not going to finish this one. So the
Oh.
pressure is 15.539.
So long as it's within a range, right? So if the
Well-
quality of water, if it's built within a range.
Yes, so what it means is temperature and pressure pressure's dependent on temperature, right? It's a dependent variable, and it only depends on temperature. So the quality doesn't affect it. If you have boiling water that's all saturated liquid or boiling water that's saturated vapor, the pressure's the same for if given the boiling temperature. So the quality wouldn't affect the answer. So it's no different than the last problem. We have a temperature, we have two pressures, and ultimately what it comes down to is this does not affect the answer in any way. The only thing it affected was it let us know it's a saturated liquid vapor mixture, that we're in the right tables. Once we've established that, if your friend had the exact same temperature but it said 0.45 was the quality, you'd both have the same answer. So we're going to do it exactly the same way. So we're trying to find this pressure here. So it's going to be T minus, I'm going to say T minus T upper over T lower minus T upper equals P minus the upper row divided by P lower minus P the upper row. So then we plug in those values and we'll get a pressure, and it has nothing to do with quality. So all the quality did was inform us that it was a saturated liquid vapor mixture. So let's try one that's a little more interesting, that actually has a quality that's it's going to affect the answer. Okay, so let's change here to problem 3. All right, again, it's water. This time we're told it's a saturated liquid vapor mixture, and we're given the specific internal energy and the temperature. So we do know it's a saturated liquid vapor mixture. I don't have to give that information because you could tell from the specific internal energy, so 971.23. If it's not in the table directly, we'll have to see how close we are. But in this case, it's right there in the table, so 70 degrees C. So we go to 70 degrees C in the saturation table. At this point, if we ignore the problem that it said it was a saturated liquid vapor mixture, we're trying to figure it out. And so we have two values. If we're in the right table, our value should be between 293 and 2469. It happens to be in between them, so we're in the right table. If it turned out that U was 9,700, then our value would no longer be between these, and it would mean we're in the wrong table. Since it's higher than it's to this side of the values, right? 7,000, that means we're in the superheat table. If it was less than 293, that means it's subcooled liquid. So when we're between the values, we're in the right table. If we're higher than the saturated vapor value, then we should be in the superheat tables. So we can tell just by the value that yes, it is a saturated liquid vapor mixture. In this problem, we were told that here. So now, I don't need to interpolate again between rows. What I need to do is interpolate between columns. So at 70 degrees, I find out that UF and UG are the values I'm going to interpolate between, and it's 293.65 and 2,469. And these are kilojoule per kilogram. So my value is somewhere in the middle, a little bit closer to this one. So that's the given U, right? So I'm going to look at this difference divided by this difference between these two values here. So the closer I am to this value, the smaller my quality will be, closer to 0. The closer I am to this value, I'll get to a quality of 1. If I go ahead and proceed and I wasn't in the range, if it's a subcooled liquid, I would get a negative quality. If it was a superheated vapor, I'd get a quality greater than 1, in which cases I was using the wrong table, and it means I'm extrapolating. So then I would know I need to redo the problem in the right table. All right, and then we have to find out what we're asking for. So what I'm trying to find, determine the quality. So quality would be defined as U minus UF over UG minus UF. So that would be 0 if my U is equal to UF, and if my value U is equal to UG, then it would be a 1. So those are the two values that I'm interpolating between. And I get that X equals 971.23 minus 293.65 divided by 2469.1 minus 293.65.
It doesn't matter that the 900, oh, never mind, I thought it was 9,000.
Right, yeah, if it was 9,000, then I'd get a value greater than 1, which should mean I'm extrapolating, which is not a good idea, and I need to go to the superheat tables. And whatever quality that is, so this is around 2,000, and this is around 600, so it's going to be a quality around 30%, something like that. So we have some idea, and it's 31.1%. It's not a bad idea to do a little mental math sometimes. Maybe you hit an extra button on the calculator, you got an extra zero in your numerator or something, and then you find out it's 300% instead of 31%, and you just quickly scan the values. So I would strongly recommend punching it in accurately in your calculator, but just doing a quick check of, yes, that's between 0 and 1, just to make sure you did things right. Okay, question 4. Now I know the quality and the temperature, and this time I want the entropy. I guess this one's a little different. So let's try this one. And
So the other one was asking for quality, right?
right. This one, 200 degrees, which is nice because that's going to be in the table. And quality of 81%. All right, so even if it didn't say it's a saturated liquid vapor mixture, I know the quality is between 0 and 1, so it's a saturated liquid vapor mixture. So before this problem even starts, I see quality. I know I'm going to go to the saturation table, and then I better find out, make sure it's water. Could be ammonia or other things that we have tables for. Refrigerant 134A, there's several saturation tables, so be careful to check that it says water, saturated water. I go to 200 degrees, which is the bottom row there on the screen, and I have, I'm trying to find entropy, specific entropy. Specific entropy is a lowercase s, so that's what I'm trying to find. I'm going to have an SF and an SG and temperature. So somewhere in the table is 200. SF, it's right here, and at the top of the table it says specific entropy, and then it has SF and SG. So if you forget the symbol for it, it is in the table. And it's, in this case, kilojoule per kilogram degree Kelvin, or Kelvin. And the values are 2.3307 and 6.4314. So they've kind of, not necessarily mixed units, but this is per Kelvin, and this is degree C. But a Kelvin, a difference, like per Kelvin and per degree C would be the same thing, because the spacing is the same, right? They're just offset by a constant. But a 1 degree Kelvin or 1 degree C change is a 1 Kelvin change, right? So I have units of kilojoule per kilogram Kelvin. So now I know the quality. So this difference, and then there's some unknown place, some unknown S here, and it's going to be this difference over this difference is what the quality is. So the quality equals S minus SF over SG minus SF. Right? And we solve in this case for S. So quality is given. So I have 0.81 equals S minus 2.3307 divided by 6.4314 minus 2.3307. And then I have one equation, one unknown. Of course, I multiply both sides of the equation by this difference. So I take that difference, multiply it times 0.81, and add this value. But if you want to write it that way, you can write that S equals SF plus X SG minus SF. And I suppose you could memorize that other form, but I just write that one and quickly derive it.
X is, like, you've been using X, is not always for quality though, right? This is just like to represent a variable, or is always, that X is always for quality?
In Thermo, X is always quality. I don't think we use X for any other variable in Thermo.
So all these ways they're all different ways of finding quality.
Yes, so turns out U minus UF over UG minus UF is equal to H minus HF over HG minus HF is equal to V minus VF over DG minus VF. So all of those things are true. Will all give us the same quality. So if I know S and I know U, or I want to find U, if I know it's a saturated liquid vapor mixture, I technically don't need to find the quality, right? I don't necessarily have to find X. I can just write, if I'm given S and I know what temperature it is, I can find SF and SG, UF and UG, and I can find U from that, right? So I can go between any parameters. In the homeworks, I start by making you find X. Then once you find X, like in the last problem, well, in this one we had X, right? We were given X, and we're finding S. If I'm given S, I can find X, right? The reverse of that. And instead of finding X, like in the last problem, I'll find U from S and the temperature. Right? So, and one of these that's coming up will do that. So, but it's important to know that all of these relationships are all the same. So don't memorize this formula and then this with this and this with this and this with this, all the separate formulas, right? They all have the exact same form. So once you memorize one of them maybe, and then know that you can put any variable in there and it will always equal the quality. Right? And then why is that? It's because we're saying it's linear between those values for any of those values. So it's a linear function between UF and UG, a linear function of quality.
Would it's the same thing? How would it work for H since H has HF?
Oh, well, it has an F and a G, right? So you can just use the F and the G and ignore that column. Or if you're clever, you say, oh, I just figured out HFG is the denominator, right?
Yeah, it's just a difference.
And so they did that one little subtraction for you. I don't know why they bothered, it just makes the tables a little more complicated. There are a lot of times that we find H more often maybe than the other values, so that's a little bit why, a little shortcut there. But it's almost not worth putting it there, especially in a textbook, because you're just trying to learn things and it just adds, where's SFG? Okay, let's try another one. And then here's the answer, 5.6523 is what we would find for S. Okay, determine the quality of a saturated liquid vapor mixture. The specific enthalpy and temperature are given. So H and T are given. And this time I want quality. I guess that's really no different. Let me just skip that one.
Yeah, I was
Just
gonna-
like just like the last one. It's just a different variable. Okay. All right. Using the following table, match the term that describes the state of water. Okay, this is a good one. This is forcing us to determine if we're in the right tables, and if we are in the right tables. So this is problem 6. Sorry, I didn't label the last one correctly, but this is 5.
I can edit that.
Or 6. Okay. So problem 6. Yeah, I think I didn't increment that in the last problem. I think we had moved on to problem 4. All right, so what we're gonna do is, if I'm told the temperature is 180 and the pressure is 12 bar, that means I'm in the wrong table, right? Because if temperature and pressure are given, they have to be, if this is given, this has to be the pressure, right? And that's not that useful. All that would tell me is it's a saturated liquid vapor mixture. If the temperature matches, but the pressure is higher, we call it a compressed liquid. We could also call it a subcooled liquid. Those two terms would apply.
If temp matches and the temperature.
And the pressure is higher, then that means it's a compressed liquid, right? If the pressure matches and the temperature is lower, we call it a subcooled liquid, right? And that's why we have the same term for the same state. So It's whether we see the matching pressure or the matching temperature. So if I have 23.179 bar and I'm told the temperature is 210 degrees, it's lower than the boiling temperature, so it's not boiling, and the temperature needs to be raised for it to boil. That means that it's subcooled, right? It's cooler than the boiling temperature, so we call it subcooled. It doesn't mean it's cold, right? Nobody's gonna get in a bath of 210 degrees C, right? You would cook, so it's not cold to the touch. It's just cooler than the boiling temperature, right? If the boiling temperature, or the temperature's given and we're told it's 220, and the pressure is 25 bar, it means, or let's say it's 33 bar, so the temperature's 220 and it's 33 bar, that means the pressure's too high for boiling at that temperature. So we'd either have to lower the pressure to get it to boil, so we call it a compressed liquid, meaning the pressure's high for that temperature. So if we brought the pressure down to 23, it would start boiling, right? 23.179. It's also like for the pressure that we have, so we say, oh wait, this pressure matches, and I go over here and it says 240, but my actual temperature is 220, then I call it a subcooled liquid, but it's the exact same state. It's 220 and 33 bar. So if I go here and find the 220 match, I see my pressure's higher, so I call it a compressed liquid. If I see this match and look at that and see, oh, this is higher than my temperature's lower than that rather, then I say, oh, it's a subcooled liquid. It's the same state. I'm describing the same state. And one student might say, that's a compressed liquid. The other might say, that's a subcooled liquid. All right, so some examples will help. So let's look at the questions. Okay, so number one, I guess the answers are right here, but 80 degrees and 2189 is specific internal energy. So I'm going to go to the row for 80 and look for 2189. And right above here, at 80 degrees, let me go to the top where we can see which one is you. So 80 degrees, and 2189 is between the values that are given there. Right? It's between 2400 and 335. So since I'm between the values, even if I'm at one of the values of the limits, I'm in the right table, right? Which means it's a saturated liquid vapor mixture. So if I'm on this table, it's a saturated liquid vapor mixture. Now, if I'm right at the value of the upper limit, then I'm saturated vapor. If I'm at the UF value, then I could call it a saturated liquid. So it's a saturated liquid vapor mixture because I'm between the values. All right, now we look at specific volume of 0.892 and 120. So I'm going to go to 120, and 0.892 is this one, and
can you highlight them?
Yeah, it's this one and this one are VF and VG. Now remember, this number's been multiplied by 1,000. So when I go to 120, this isn't 1 and 892. This is 00106 and 892. But I happen to be at the upper limit, which is 0.892. So this would be a saturated vapor because I'm at the saturated vapor value. Not above it, right at it. So that's a saturated vapor. Now I'm going to go to 101.325 and 2014 for the enthalpy. So 101.35 is right here. And the enthalpy again was 2014. So an enthalpy that is between 2600 and 400. So and then this HFG is just the difference. So I'm looking, is it between this value and this value? And I have to skip over this one in the middle. Again, that one in the middle is the difference. So my 2100 is between those two values, so it's a saturated liquid vapor mixture at that time.
So if it's in between values, saturated liquid vapor.
Yes. Okay. 23.179 bar, which is right here. So that's the row I'm on. So we know it's 220 degrees. And 985.4 this is UF, this is UG, and it's slightly above the saturated liquid value, but it is above it. So it's a saturated liquid vapor mixture between UF and UG. If we go up here, so here's UF and UG at this pressure, 23.17. So again, saturated liquid vapor mixture. I think they start getting a little more interesting, either this problem or the next. So 15.539 bar, we have that one here, and an enthalpy of 852.46. So we go up here, 852.46, we're at the saturated liquid value, so it's a saturated liquid. I guess these weren't that interesting. 46, we're right here. So 46 bar, 0.887, and then the internal energy 2598.5. That's one of our limits. Let's just see what that is. That's UG. So this is saturated vapor also.
What do they give you, specific volume and a specific internal energy?
Okay, so if one of them isn't temperature or pressure, then you're going to have a little trouble because you'll have to like kind of figure out from both of them. So they're both in between saturated liquid vapor mixture. It gets a little tricky. So I may have one of those. Sometimes you'd have to go to the superheat tables just to verify that that it's not superheat. We can see if, did you have one like that maybe in the next problem?
Yeah, I have one right now.
Okay.
I have two that gives us quality.
On problem 6?
Yeah.
Okay, so, all right, so the question was, all right, we have a specific volume given and
147?
0.127?
Yeah.
Okay, and
Specific internal energy. 2,594.8.
okay, so 0.127. Okay, so we kind of lucked out. It's one of the, so it's the VG value, right? So this happens to equal VG, right? And so then the 2594.8, let's see, where was that one? So,
Yeah, that UG.
yeah, so right here, right? And it happens to be at the same row, right? So this one equals VG and this one equals UG, so it has to be saturated vapor, right?
And I have two with quality. If X equals 0, it's a saturated liquid, right?
Right, so any problem where X equals 0, it's a saturated liquid. It doesn't matter what other property you give.
The other one is X equals 1, that'd be
Right?
saturated.
And if it's X equal 1, you don't even need another property. It's a saturated vapor. So where this would get tricky is if V is between VF and VG, and then U is outside the range of UF and UG. It's possible that it still could be a saturated liquid vapor mixture, just depending on how close you were to UG.
If it's, we'll have to interpolate if it's not UG.
Right, you'd have to do linear interpolation and figure out what would UF and UG. Well, you can usually tell by going to the superheat tables and then finding out, like interpolating there and find out, no, it has to be, like it doesn't match the superheat values. But anyway, we might have one of those. We'll look at it if we get one. If we don't, I wouldn't worry about it too much. But we can come back to it later. Okay, now on to the superheat tables. So question 7. All right, it's really, it's the same kind of interpolation problems. The tables are just laid out a little differently. So now we have the pressure and the temperature given, 400 kPa. And a temperature of 242.9.
Yeah.
Okay, and so in this case, we have 4 bars, so we're in the table on the right. This is like the 1-star problem I talked about in class, so this is pretty straightforward. You just use this tables can be ignored, right? So we're good, we have a table for that, and then we just find 242. Of course, we have to interpolate. So we interpolate between 240 and 260. So we have, the table has 400 kPa, which matches, and we have the temperature is 240, 260, and we're at 242.9, so we know we'll be close to the value, and we're trying to find what in this question? Specific internal energy, so U, so the 3rd column. And we have 2709.9. And 2741.4. And so we're trying to find this value. And so, you know, if this is the upper row and this is the lower row, then we have T minus T upper over T lower minus T upper equals U lower, or sorry, U minus U upper over U lower minus U upper, right? Which is the exact same thing we did with saturation tables when we're between temperatures, so it's no different than that. And we know everything on this side, and the only thing we don't know is U. So you could write that as U equals U of the upper value, that account plus T minus T upper over T lower minus T upper times U lower minus U upper. So the same equation, it's just written differently, right? We solved it for U. So it's very similar, and we were calling this when we were using, like when we were finding quality, like when we have, like this was F and G, and now it's U and L, right? So it's very much like the value plus the quality times the difference. So all of these are very similar. You should maybe make those connections, because then it's easier to remember the different formats. But so we plug in the values, and we should get the same specific internal energy that's given in the problem, 2714.5. And then just to make sure, you look and see 2709, 2741, and we ended up at 2714, but we were very close to this value, so it makes sense that our answer is very close. If your answer is very close to this one, what happened is one of these values you switched. You did the upper and the lower on one side and the lower minus the upper. All right, this one probably similar. Pressure and temperature are given. This time, not sure if I can scroll to the right. So the pressure is 300. So now we're on the other pressure value. So we're using this one. And that would be the exact same thing. This one, we're 300 again. 300 again, so these are all kind of the same problems. We're just finding different things, specific enthalpy.
There's no like those 2-star problems or anything like that, right?
Not yet. Now we have 400 again, then we're finding U, or we're giving U in pressure, we're finding temperature. So what I wanted you to know in this one is you don't have to be given temperature. You can find, okay. So you can be given pressure and entropy, or pressure and internal energy, and find temperature. I think up to this point, pressure and temperature were always given. That might be the 2-star problem. All right, this one is a 3-star problem probably. So this is, we're given pressure and temperature, but well, no, this isn't too bad. One of the values is given, so pressure I have to interpolate. So let's just look at this real quick. We had been interpolating on temperature, now we have to interpolate on pressure. So up here on question 12, so the pressure is between 300 and 400, so it's 387.6, and the temperature is 260. So this time, we're on one of the temperature rows, but we're in between the two pressure tables. So we have P equals 300, P equals 400. In this table, there's a T equals 260. And over here, same thing. And then there's also, we're trying to find specific volume. So there's a specific volume given under the 4-bar problem, and it's 0.6071. And on the 3-bar table, it's 0.9067. The problem is, we have a value for this pressure and this pressure, but our pressure is somewhere here at 387.6. And this is a pressure of 400, and this one's pressure of 300. So we're most of the way to 400, but not all the way there. So our value will be between those two pressures, so the specific volume will also be between those two values. So just like before, instead of doing upper and lower values, so let's call it like 4 and 3. So we'll call this 4 and this 3. So I'm going to put that P minus P3, so that's this pressure minus that, equals, or divided by rather, this pressure minus that one. That will give me a ratio between 0 and 1. And then we have is equal to V minus V3 over V4 minus V3. So just make sure that you're, whatever you're using to describe it, if this is upper and lower, or 4 and 3, or left and right, whatever you want to use to help you remember which values you're using from the table, that those subscripts describe the same thing. And then what I'm given was P, so I have 387.6 minus 300 over 400 minus 300 equals V, which is my unknown, minus 0.9067 over 0.6071 minus 0.9067. And this is generally where students have a problem, is this was the larger minus the smaller, but here it's the smaller minus the larger. That's correct. You don't do the larger minus the smaller. You do the one from this table minus the one from this table. So it's in the denominator, it's the one from the right table, from this V4, if I called it V4, right? And this V3. So you just have to be careful. So this is a good example of where if students are always in the habit of just taking the larger minus the smaller, you're going to get into trouble here. And then we solve for V in this case. And then again, it will be V equals, in this case, it'll be V3 plus P minus P3 over P4 minus P3 times P4 minus P3, which is just, with algebra, just rearranging this equation. Of course, you could just do it with the numbers and do the algebra with the numbers as well. Okay, I think that's probably considered a 2-star problem. All right, then the last one, calculate the specific enthalpy of a substance giving the following data. So This is just to remind you that enthalpy equals U plus PV.
Problem 13.
Yeah. And so specific enthalpy equals specific internal energy plus pressure times specific volume, or enthalpy equals internal energy plus pressure times volume. So those are both true because all I have to do is divide this by M and I get the first equation. So both of those equations are valid. So I was asked for the specific enthalpy, which is the first equation, and I was given U, the specific internal energy, the pressure, and the specific volume. So if we write those out, we get 2817, and we better write the units out, kilojoule per kilogram, plus the pressure, which is 2.12 bar, times 0.852 cubic meters per kilogram. Now, we have to be careful that the units of this have to match the units of this if I'm going to add the two quantities together. So bar cubic meter per kilogram, we don't know if that's equivalent to a kilojoule per kilogram. So, and I know in fact that it's not. So I'm going to try and convert that to kilojoules per kilogram. Really, bar cubic meter is the only thing I have to convert. So sure. All right, we'll do here. Okay. We're going to try and match our kilojoule per kilogram to bar cubic meter per kilogram. Maybe they're equivalent, but if so, we have to prove it. If they're not equivalent, then we need to convert to consistent units. So 1 bar is equivalent to 100 kilopascal. And we'll do 1 kilopascal is equivalent to 1 kilonewton per meter squared. Right, so the kilopascal will cancel. And then I have cubic meters in the numerator and meters squared in the denominator. So those two will cancel 2 of these, so it'd really be 3 minus 2, which I can just get rid of it, and it's meter by itself, meter to the power 1. And I have kilonewton meter, so 1 kilonewton meter is equal to 1 kilojoule. And so just to be clear, in your definitions, 1 joule is 1 Newton meter, so 1,000 joules is 1,000 Newton meters. So that often I'll write it just with a kilojoule, kilonewton meter, and then I get my my kilonewton and my last meter cancels with the kilonewton and the last meter, and I have kilojoule and I still have kilogram, so now it's the same. So then now we look, did it change anything? Yes, it's times 100. Sometimes, if you want to take a shortcut, and you know that if this was in kilopascal and that was in cubic meter, then this can be added to that. Technically speaking, it would be clearer if you show that, but on an exam, if you do it right, I will allow you to do that way, of course, if it's online homework. It doesn't know how you did the units. What I won't do is, if you show this and you make a mistake, I'll give you half credit, if, at least for that part of the problem. If you don't show this and you get it wrong, if you just put 2.12 bar times this and add the values together, I'll give you no credit for the units, right? So you, at least this way, by showing that, you're at least getting credit for the units. So it's safer until you're careful and can know when you have equivalent systems of units, then I would strongly recommend writing it out like that. Okay, that's the last problem in homework 4B. Hopefully that was of some help to you.